Imagine that everything we know about the universe is missing a piece. Scientists have measured the expansion of the universe for decades, and today they have a problem. Two different methods, two different answers, both appear correct, yet they completely disagree. Some scientists believe this could reveal new physics, others wonder if our understanding of the universe is incomplete, and a few have proposed something even stranger. What if we are living inside a vast cosmic void, or perhaps between two different universes? This is the mystery known as Hubble tension. To understand this mystery, we must travel back to the year 1916. Europe was being torn apart by the First World War. Millions were dying. Yet on the Russian front, a German soldier spent his spare moments doing mathematics. His name was Karl Schwarzschild. Only months earlier, Albert Einstein had published his revolutionary theory of general relativity. It described gravity not as a force, but as the curvature of space and time itself. Einstein's equations were powerful, but there was a problem. He couldn't find an exact solution. Schwarzschild could. While serving in the middle of a war, he solved Einstein's equations and mailed the results to Einstein. Hidden inside that solution was something terrifying. It predicted an object so dense that space and time would collapse inward, a place from which nothing could escape, not even light. Today, we call them black holes. Schwarzschild died shortly afterward, but his work would become one of the foundations of modern cosmology, and eventually it would help lead us to one of the greatest mysteries in science. Now, let's jump to the 1920s. At that time, many scientists believed the entire universe was just one galaxy, the Milky Way. Then came a debate. Were strange objects like Andromeda simply clouds inside our galaxy, or were they entire galaxies of their own? No one knew, because nobody had a reliable way to measure cosmic distances. That changed in 1923. Astronomer Edwin Hubble was studying Andromeda when he noticed a special type of star, a Cepheid variable. These stars brighten and dim in a predictable pattern. By measuring that pattern, astronomers can determine their true brightness. And once you know how bright a star really is, you can calculate how far away it must be. Hubble did the math. The results shocked the scientific world. Andromeda wasn't a cloud inside our galaxy. It was an entirely separate galaxy, millions of light years away. Suddenly, the universe became far larger than anyone had imagined. Hubble continued measuring distant galaxies, and he noticed something remarkable. The farther away a galaxy was, the redder its light appeared. This effect is known as redshift. It happens because distant galaxies are moving away from us, and the farther they are, the faster they seem to move. The universe wasn't static, it was expanding. Hubble turned this discovery into a mathematical relationship known as Hubble's law. And from that law came a crucial number, the Hubble constant, a value that tells us how fast the universe is expanding. For decades, scientists refined this measurement using increasingly powerful telescopes. And eventually they believed they were getting close to the answer. But then the answers stopped agreeing. Scientists use one method by observing nearby galaxies. They measure distances using Cepheid stars and type I as supernovae. These exploding stars act like cosmic standard candles. Known brightness, known distance. Using this method, researchers measured the Hubble constant at approximately 73 kilometers per second per megaparsec. Then another method arrived. Instead of looking at nearby galaxies, scientists studied the oldest light in the universe, the cosmic microwave background. This ancient radiation was released roughly 380,000 years after the Big Bang. It is essentially a baby picture of the universe. Using data from the Planck mission and applying the standard cosmological model, scientists obtained a different answer, around 67 kilometers per second per megaparsec. Both measurements were repeated. Both were carefully checked, yet the disagreement remained 73 or 67, two numbers, one universe, and no clear explanation. At first glance, a difference of 6 might not sound important, but on cosmic scales, it becomes enormous. As distance increases, that small gap grows larger and larger. Across billions of light years, the disagreement becomes thousands of kilometers per second, enough to change our estimates of the age of the universe, the size of the universe, the history of cosmic expansion. This isn't a tiny error, it's a crack in our understanding of reality. Scientists call it Hubble tension. Researchers tried alternative methods. Some measured water masers orbiting supermassive black holes, others used gravitational lensing, where massive galaxies bend light from objects behind them. Remarkably, many of these independent measurements continued pointing toward values close to 73. Yet observations based on the early universe continued favoring around 67. So what is happening? Some scientists propose unknown forms of energy. Others suggest new particles. Some question whether dark matter behaves differently than expected. A few even wonder whether gravity itself changes at enormous scales. And then there is one of the strangest ideas of all. What if our region of space lies inside a gigantic cosmic void, a place less dense than the surrounding universe? If that were true, our local measurements could appear different from measurements made using the universe as a whole. Some versions of this idea go even further, suggesting that what we observe may be influenced by structures beyond our visible universe, perhaps even something resembling neighboring universes. At present, there is no proof for these ideas, but the mystery remains unsolved. Today, new observatories are searching for answers. The Euclid mission is mapping the structure of the universe in unprecedented detail. Meanwhile, gravitational-wave observatories such as LIGO are providing entirely new ways to measure cosmic distances. Perhaps the answer is hidden in new physics. Perhaps a crucial piece of the universe is still missing. Or perhaps the cosmos is stranger than we ever imagined. What do you think? Why do two of the most precise measurements in modern astronomy disagree? Leave your thoughts in the comments below. If you enjoy exploring mysteries like this, from black holes to the deepest secrets of the cosmos, subscribe to factsobal and join us on the journey. Because for now, the universe continues to guard its secret. And somewhere between 67 and 73, the truth is waiting to be found. Until then, we keep looking.